everyone. My name is Bonnie, and thank you for joining for today's webinar, Symbolic Approach to Controls Engineering. Engineering systems today are becoming ever more complex, and the use of computational tools for control design is pretty much inevitable in the industry. And we at MapleSoft believe that symbolic computational tools can provide numerous benefits in the controls classroom, and I'll be spending the next 40 minutes or so presenting some of these benefits. So let's first begin with some of the challenges that we've been hearing from controls educators. First one, it's hard to keep students motivated and engaged, especially with increasingly tight time constraints. Controls course content is math heavy, and there's a lot of topics to go through. Plant modeling, linearization, open loop versus closed loop, properties of various plots, PID feedback controllers, time domain, frequency domain, and then how to tie all of those concepts together. So there's a lot of concepts we have to present to students. Unfortunately, what that means is educators don't get to spend a lot of time motivating students. A lot of times we try to motivate students at the beginning of the course, but we start losing sight of that aspect as the course progresses and the theories get more and more involved. And ironically, typically that's when students need the most motivating. The second one, disconnect between mathematics and reality. As the semester progresses and you get deeper and deeper into controls, students start focusing more and more on the math and a lot of times what is required to pass the course. And then educators start presenting concepts to students starting from an abstract transfer function to save time. As a result, students start losing that connection with the real-world system. The last one I want to talk about, computational tools. Graduates with experience using computational tools for control design is no longer just a bonus for the controls industry. It's really becoming a requirement. So what that means for an educator is that on top of the heavy course content that they have to teach, they also have to teach products. So how can symbolic computation help address the above issues? This will be the topic of today's webinar. Can a symbolic tool provide more effective use of a professor and a student's time while we enhance learning and understanding? Can it help engage students? I've broken down today's webinar into 3 sections. First, I will talk about how educators can take advantage of acausal modeling together with Symbolics to engage students, but while keeping the math and the physics that's involved with the systems front and center. I will then discuss controls design capabilities within a symbolic tool named Maple and do an in-product demonstration. Lastly, I'll present how these can be integrated with hardware in a controls lab for the controller testing. So let's begin with the first chapter of any intros controls course, plant modeling. Let's take a look at how one would do this using a traditional signal-based tool. In the example I have on screen, this is a double mass spring damper system, so very typical to model a quarter car vehicle suspension. The first step we would take in order to derive this model is to derive the equations of motion for the 2 masses. We would then simplify the equations and manipulate it into a form such that we can enter it into an environment like this on the right-hand side. Now, in this diagram, you'll see that the components being used are essentially mathematical operators put together to represent the equation that was derived. This graphics clearly reminds students of the equations that they just derived, not of the actual vehicle suspension, because the structure of this diagram reflects the calculation procedure. Now, using acausal modeling, the components that are being used to model the system are physical components. So components like springs, dampers, resistors, hydraulic cylinders, and so on. As a result, the model is intuitive to build, it's visually representative, and it provides insight on the actual system structure, as you can see the resemblance between the A-causal model, and the model schematic. On top of that, modeling in this environment motivates a student to actually explore the system. For example, what would happen if they added more springs in series or in parallel to the system? To test out this theory, they would just pull in those components and connect the ports of the components together accordingly. Whereas in a signal-based environment, they would have to basically rederive the equations from scratch. In this environment, they can test out many of these similar scenarios very quickly, and these activities encourage deeper understanding of the engineering system being controlled as the plant model is being developed. So it can engage students right from the get-go with real-world applications. This suspension system is something that most students will understand. On the industry side, A-causal modeling is becoming the industry standard as its benefit over signal-based modeling is becoming more and more apparent. On the education side, for students, you'll notice that in this type of environment, students don't actually derive the equations. And for a student, deriving those equations of motion for a system is beneficial for the first few times. They get a sense of the importance of their ODE classes. They gain an appreciation for how equations are used to describe performances of real-world systems. However, after doing this for a few times and they've grasped those concepts already, the benefits of an A-causal modeling environment far outweighs that of a causal environment, where students waste time manipulating equations and doing number crunching. Now, A-causal modeling, together with a symbolic environment, extends the capabilities even further. A-causal plant modeling is great, but what about the important math that's behind it? With a symbolic tool, the equations can be extracted automatically, as you can see on the screen, and it's extracted in a symbolic form, just as a student would see from a textbook. This is very useful as we continue to other aspects of the course where we typically start with a transfer function. In a symbolic computational tool, no matter where you are in the course content, you can always start with a real-world system, present the symbolic equations immediately without having to derive them and taking a lot of the course class time. We can then continue directly with the control topic. So students don't have to derive those equations anymore because the focus is now on a different chapter at this point. But they're still constantly aware of the engineering system that's being controlled, why it needs to be controlled, and the equations that govern the behavior. So I really think that this confirms the importance of equations as well. One other point is that a lot of times we don't go into software tools until near the end of the course because we still want to look at the equations in a symbolic form. We want to see what parameters are having what effects in the equations. Are they in the denominator? Are they in the numerator? And by introducing software at an early point, it basically means numerical substitutions, and we lose that. However, in a symbolic tool, this basically becomes an irrelevant concern because at every stage of a problem, the system can be solved numerically or symbolically. So we have a choice. In this slide here, we are introducing the topics of observability and controllability, and this is still in relation to our quadrocopter model that we started with. Again, this is a model that most students can relate to. It's not a trivial transfer function that we had to resort to because the matrices that we would generate would have taken too much time to develop in a classroom. So being able to work with these in a symbolic tool is a huge time saver. It helps students focus on the concept that's being taught instead of getting lost in the techniques and the mathematics. So in this case here, we're trying to share the idea of what is a controllable system, what is an observable system, how to determine if it's controllable or observable, and what is really the significance of it. These are the concepts we want to teach, not necessarily how to manipulate the equations. And a natural extension to A-causal modeling is that the libraries are multi-domain. And this is, of course, very useful as real-world systems are always multi-domain. So students get to grasp fundamentally how domains are working together within one environment. Okay, now I'm going to jump into a product demo to give you an idea of how the product works, how we do plant modeling, and some control design techniques or tools that we have. So this here you see on the screen is MapleSim. This is our modeling and simulation tool. I'm going to begin with building a simple model. This is our product library. If I open up my multi-body library, I'm going to start pulling in a few components to model a pendulum. And I can zoom in on my 3D view, and you can see that as students are pulling in these components, they can immediately see components being added in the 3D visualization. So here, for example, I'm adding a rigid body, which allows me to define my mass and rotational inertia and initial conditions. I'm going to add a revolute joint to give my pendulum the hinge motion. And as I connect these components up, you'll see that in the visualization, my pendulum being built. So there it is. One more thing before I run the simulation, I'll just add a probe so I can extract some information out to plot. In this case, I'm going to just look for the angle, plotted versus time, and I'll run the simulation. So very quickly, we have our results for the pendulum, as expected. And in the 3D visualization, we have our pendulum swinging back and forth. Now let's say I want to expand on this. I can easily make this a reusable subsystem, this link that I've just created. If I double click on it, again, I get the full details of what I had just created, so it's not lost. And what I can do on top of that is actually parameterize my model instead of using all numerics. So I can say that this component here is a coordinate transformation. I'm saying that it's L over 2 in the x direction, L being the length of my link, and then I'm going to parameterize my mass as well. Once I've defined those relations, I can actually define my parameter values, so L and M. Now I'm going to step back out to the main level of my model, and you'll see that if I click on this component, my link subsystem that I've created, I'll have these parameters available to me. Now I can create copies of these and start making 2-link or 3-link pendulums. I can attach different probes at any location in my model, so students can explore that way. In this case, I'm going to add a probe to the end of my 3rd link and ask for the XY position. And again, I'll run my simulation. Actually, sorry, before I run the simulation, I'm going to change some of the parameters to make this a little more interesting. So let's say the first pendulum, a length and mass of 5, and then 3 and 1. So we can easily change the parameters and investigate the characteristics of our system. And again, we'll see 3 plots this time. So first, my first probe that I created in the beginning, my angle for my first joint, and then my X and Y for the end of my 3rd link. If I zoom out here, I can play the simulation and see what is happening. So there's my 3-link pendulum. This right now is acting purely due to gravity. We can then start going into different libraries and actuate this pendulum. So for example, I'm going to go in the electrical library and pull in a simple DC motor. And I'm going to actuate the first joint. Okay, I'm going to give a voltage source. You see that I can start working in different domains immediately. And the different color in the connection lines and the ports indicate the different domains. So students are always aware what domain they're working in. By attaching a probe this time in an electrical circuit, you'll see the information that's available to me changes accordingly. So this time I'm able to extract voltage and current through my circuit. And let's run the simulation again. This time the pendulum should be actuated, or should be powered. Okay, we see different results, and let's give a bit more voltage here. Let's do a 60 volts. Okay, there we go again. Okay, so students can easily explore their system, and it's an easy and intuitive environment to do so. The second example that I wanted to show is in Maple. So this is our symbolic computation tool. You can see that on top of, so this is where we do the analysis, where we would do the control design, the math. But with on top of all of those functions, the math capabilities, you'll notice that the documentation, it has a very rich environment. And what I mean by that is you'll see combinations of text, images, links for quick navigation, equations being solved, parameters for organization. So course contents can actually be presented in this single interactive environment. I say interactive because we have embedded components that are used to make this worksheet interactive. In this case here, students can vary the theta and omega values to see what their step response would be. We also have something called code edit region where you can embed code within the worksheet. It's collapsed so that it doesn't ruin the flow of the document. So here we're explaining the design of a P controller, a PI controller, a PID controller. So again, being able to vary these with various embedded components and immediately seeing the response. So as they're learning the material, students are learning a widely used computational tool as well. The next example I'm showing is a control system design tool that's provided directly within Maple. This is a very useful tool that allows us to, once we define our system, compute different things very quickly. For example, characteristic polynomial, controllability matrix, observability matrix, gain margin, phase margin, and so on. In the next area over, we're able to plot various things. So, for example, a response plot, root locus plot, a phase plot. So, various plots you can quickly choose to display. The last one I'm going to show is really the integration between MapleSim and Maple. So we can do the plant modeling within MapleSim. MapleSim and Maple are tightly integrated together. So we can extract the equations of any system that's modeled within MapleSim. And then we can start doing analysis with it. We can start making use of tools like what I just shown. So Maple is a very open environment, and what that allows is the creation of customized tools. This example is an example created by the Application Engineering Group for a Surface project. Here we have a simple spring damper model. This is a nonlinear damper, actually. What we have is created a PID tool where after we've done linearization, this is our resultant transfer function plant that represents our plant. We can then click to generate the system. Again, we can see various plots. This is based on our drop-down menu here. We can choose to see it either in open loop or closed loop. We can get important information out of our plots, such as final value, rise time, peak point, settling time, gain margin, space margin, and so on. And in the second row, we have the actual control design, and it's divided into 3 sections. So the first being able to use auto-tune methods. So for example, if I wanted to use the Cohen-Kuhn method to design a controller, and let's take a look at the response plot in closed loop. So we can again vary these sliders and see how that changes our response plots, our root locus, and our Bodie plots. Or we can also select different types of controller that we want to design. Or we can use the second method, which is a manual PID method. So here we're by default starting with PID gain values that are calculated using the auto-tune method, but once we have that, we can start again varying the PID gain constants and seeing how our system will respond. And the same is with pole placement, where we can choose to add or remove real or imaginary zeros and gains to our system. Once we're happy with the response, we can then hit this button to generate a MapleSim component directly. So that would be a component that represents the controller. This is the controller that was created, and we've put it inside a feedback control loop. And I'll run this simulation. So we'll see the response to a step input of 0.1. Okay, going back to my presentation. Beyond these tools that I've shown in the product, there's also an extensive command library for control design. In this example, I'm showing quadrocopter motion control. We're designing an LQR controller in this case. So this is the system. We have our main body, the 4 rotors. Within each of these subsystems, there are 4 DC motors that are powering the system. The inputs to this system are the rotor's motor voltage, so that's for each one. And then we have a set of outputs. The first set representing the center of mass position, then the center of mass orientation, the rotor speeds, and then the angular velocity. Once we have the plant modeled within MapleSim, we can extract those equations and perform linearization. Then we can begin using commands within our control design package. So in this case here, I'm using compute QR to obtain the weighting matrices based on a desired time constant. So in this case, 0.2. We can then use the LQR command together with the computed Q&R matrices from the step above to calculate our state feedback gain. We can then put it into a closed loop system so that we can test the performance of our controller. We're testing it with a step signal of 0.2 in this case, and we're plotting the XYZ position of our center of mass. Next, we're going to add a common filter. So the first step in doing that is to generate covariance matrix for the state and measurement noise. The first matrices here is a big size, so I've just chosen to browse the structure of this matrix through an image so we can have an idea of what that matrix looks like. We could then use the common command to design the common estimator given those state and measurement matrices. So the first output that we're given is the gain matrix, and then we're also given the solution to the Riccati equation. The last step, we can use this command controller observer to combine the controller and the common filter and essentially create an LQG controller. And again, we'll apply the same test as previous. So plotting the XYZ position of the system with a step input of 0.2. We export the controller into MapleSim so we can run a simulation. And here I've included a video of the quadrocopter in motion. The next example I'm sharing is one of gain scheduling. So this is, the plant is an inverted pendulum on a cart, so the well-known system. The problem here is how do we control the force on the cart such that the pendulum that's hinged on this cart can be balanced. So this is a well-known system to explain linearization and to do linear control design. So this is the first step that we took. So we designed a PID controller, and that's based on a linearized model about theta equals 0. This block here is for disturbance. Right now it's at 0. And what we're plotting here is the performance of this inverted pendulum on a cart, but instead of just a stability problem, we're doing one of position control. So we're actually changing the desired angle, you can see in the input here, so that it's increasingly getting further and further away from that linearization point, theta equals 0. And you can see the decreasing controller performance as we go further and further away. And now if we turn on the disturbance, you can see the system goes to instability. What we've done is implement a gain scheduling example controller, and essentially what this block here is a series of PID controllers, so 3 linear controllers that were designed about different linearization points. They were implemented as lookup tables, which then interpolate between the PID gains based on the scheduling variable. So that will determine the current operating region. Based on that, again, we plot our results of the simulation, and you can see that the performance is much more consistent throughout. And once we add the disturbance, we can see that it is still being controlled versus the case with the linear controller where we go to instability. Okay, and beyond these tools that beyond the examples that I've shown, we have capabilities to do other type of control design. For example, feedback linearization, parameter estimation, adaptive controls. I've just shown a few of our examples. We also have a model gallery on our website, which we frequently post new material on. These are some of the examples or control-related examples that are on there. There's also a dedicated academic control section for all things academic. And outside of the academic section, of course, students can at any point download other models that interest them to see how it was modeled and how different types of analysis was done. Okay, the last topic I wanted to talk about in today's webinar is how everything we've talked about can be tested with hardware. What I'm presenting here is an example lab project. We have the schematic of the hardware to be modeled. This is what it would look like in a signal-based tool. We have inputs, outputs. The system is essentially reduced to this transfer function. This is the system modeled in MapleSim. The structure is completely exposed. We have our electric circuits, we have our mechanical components, we have visualization. Students can experiment with the model immediately. The equations, again, are extracted symbolically. From here, they can incorporate the control theory, use the rich documentation environment that I've shown previously, and generate controllers. They can then test the controller within simulations. In this case here, I've taken a screenshot of testing the controller for position control, velocity control, and I've also compared it with the full model dynamics versus the transfer function. These are the results. Now let's test how the controller works with hardware. So I've exported the model into LabVIEW. In this screenshot here, you'll see that I've actually done 3 comparisons. The first model here, the controller was implemented, and it's actually interacting with hardware. The second one is the same controller. It's now controlling the transfer function representation of the plant. And in the third case, same controller, and this is the model exported from MapleSim. Okay, and these were the results. In this simple case, you can see that the results from the transfer function, so that's in red, versus in MapleSim, are pretty close. However, you can imagine that for more complicated systems where assumptions have to be regularly made to simplify problems when we solve equations by hand, that some of those dynamics would be lost. And these dynamics can create an interesting discussion point in class as well. The example that I've shown in this example was a Quasar rotary inverted pendulum. I'll just play the video of the hardware. Quasar has a wide range of modular classic control plans for educational purpose. And many of the models for these modules have already been developed within MapleSim and are freely available in our model gallery. So these are some of the models that we've created that are Quasar modules. And in this example, the hardware connectivity was done through exporting MapleSim model into LabVIEW, and then real-time testing was done. We have many other connectors that allow users to export to other platforms that are currently being used in your lab. Okay, in the beginning of today's presentation, I presented some of the challenges that we hear from controls educator. Hard to keep students motivated and engaged, a disconnect between mathematics and reality, computational tools being a requirement, and so educators have to teach course content and on top of computational product. In today's webinar, we've looked at how in a symbolic tool like Maple and MapleSim, its intuitive and natural approach to plant modeling. It really motivates students to explore real-world systems and understand the need for controllers right from the beginning of the course. This is in the first 1 or 2 weeks. Contents that are presented throughout the course can always have a real-world connection because the model schematic is there and the equations are automatically generated, which means the disconnect between math equations and the system is significantly reduced. Symbolic computation environment also encourages students to spend more time exploring and understanding theories and their system instead of spending the time doing number crunching. And because of the symbolic nature and the rich documentation environment, the tool can be integrated throughout the course. This allows students to simultaneously gain a deeper understanding of the engineering system, the control theory, and the industry computational tool. Okay, and that brings me to an end to today's webinar. Thank you for joining.